All right, I'm going to get started. Hello, everybody in absentia. So, well, anyway, take one. I hope this works. So today we're talking about rings of integers. So it says week 1 up here, but I guess this is really week 2. So we're going to sort of try and understand what it means to talk about the integers, not sort of in the rational numbers, but in some finite extension of the rational numbers. So I'm going to say let K over Q be a finite extension. Maybe I'll just write this. Okay, and then I'm going to define O sub K is the set of elements A and K such that the minimal polynomial has coefficients in Z. So the minimal polynomial is the smallest degree monic polynomial satisfied by that element A. So I'm denoting it M sub A. And I'm asking that it have coefficients in Z. Okay, so that's what we're going to mean by the integers. And just to recall an example that was on the exercises last week, if n is square free, so n is a square free integer, so it's just not an integer that's not divisible by sort of the square of any prime number, then if we look at the ring of integers in Q square root of n, well, it's going to be equal to the following. It's going to be equal to just Z adjoint square root of n, which is just Z plus Z times square root of n. If n is congruent to 2 or 3 mod 4, and it's going to be equal to Z 1 plus square root of n over 2, which again, in this case is just the Z module spanned by Z and 1 plus square root of n over 2. So here in this notation means smallest ring containing Z and square root of n. This means smallest subring containing Z and 1 plus square root of n over 2. Then here this is sort of saying that as Z modules, like this is a spanning set, so 1 and sort of square root of n. If n is congruent to 1 mod 4. This is something we sort of saw an example in the introductory lecture in a special case, and then was on the exercises to work out in general. Okay, and so, well, what's easy to check in this example is that, in particular, sort of the integers by this definition, which again we could compute because it's easy to, and we can compute the minimal polynomial of any element here. And so because that was something we can compute, we can write down what these are, and then you can just check that like this is a subring, like it's preserved under addition and multiplication. Okay, and so this is not synced up. So I'm resetting this screen share. I never have issues with this. So hopefully this isn't a persistent problem. So the big theorem of the week is is a different color. So 1, so if K over Q is a finite extension, then, well, the first thing is just that if I take the ring of integers, so the integers, and I multiply them by q, then I get everything. So this sort of, in some sense, says that nothing is too far from being an integer. It's just a matter of some denominators you can clear. And definitely, you can sort of see that in this example. The second, so that first part is basically trivial. We'll show it in a second. The next, and the less trivial and more interesting part is that OK is a subring of K. And so let me just point out, if I combine these first two, then in particular, the fraction field of OK is equal to K. So, and somehow that's good because that's like one of the basic properties of the integers. The fraction field of the integers is the rational numbers. And so, well, we'd like to have the same kind of statement. But good, okay, so it's a subring. So I really, you can sort of multiply and add two things. And again, I mean, I mentioned this in the introductory lecture, but this is, I mean, it's not obvious from the definition because like minimal polynomials don't necessarily behave well with respect to adding and sort of multiplying elements. So there's really something to be seen there. Okay, so 3, OK is integrally closed. So I'll come back to that in a second. Say more about what that means. And then 4, OK is a free Z module. So just as a module over the integers of rank equal to the index of K over Q. So the degree of this field extension is the dimension of K is a Q vector space. And here we're sort of saying that's mirrored at the level of integers. So the ring of integers in K is a free module of rank so that same rank. So that's the module analog of this vector space statement. Okay. Good. So let me just make 2 remarks. So this integrally closed, this essentially says you're not like, you're getting everything you can in sort of one step. You don't have to sort of take everything with a minimal polynomial in Z and then sort of add to it everything that now has sort of a minimal polynomial in OK, and so on. So somehow that's what that's saying. This is sort of a one-step process. And like, this also means that you could think about like chains of field extensions. And like you would sort of say like, you could say ask whether having like if L is over K is over Q, you could ask like whether having a minimal polynomial with coefficients in OK for an element of L is the same as sort of its minimal polynomial over Q having coefficients below Q. And so this basically says that's going to happen. Okay. And we'll come back to that in a minute. And then 4, I mean, it's sort of no surprise that the module is free because it's a Z module and it's torsion free because it lives inside of a field. So it's no surprise that it's free if you know it's of finite rank. And then sort of once you know that's free of finite rank, you sort of combine with part 1, like getting that this degree is not hard. So actually, I mean, sort of the a little bit subtle actually when you first think about it. So the hard part is to see it's finally generated. So, and if you knew it was finally generated, then you'd get this, but it might not be. I mean, like sort of K itself as a Z module is not finally generated. I mean, Q as a Z module is not finally generated. And so you have just something inside of here and it may or may not be finally generated. So you sort of need to make some argument to see that it is. And I mean, I should say in property, yeah, so 1 is elementary. Again, I'll prove it in a second. So 2 to 3 are basically general sort of follow. These follow from much more general statements that we'll talk about. So, and so there's a theory of integral elements for arbitrary extensions of commutative rings, and 2 and 3 are just special cases of results in that world. And then 4, it's really, it's not in, it's more general than this, but it's sort of uses something special. So it's special to our situation. Sort of in the sense that if you keep on doing enough number theory, like sort of doing enough arithmetic like this, like you can quickly run into situations where actually this kind of thing isn't true. So for example, I talked briefly about this kind of thing in my class last year for anyone who was there. Okay, so then the outline for the rest of the talk, well, first we're going to prove 1 because it's easy. Then we'll sort of set up the more general statements that give 2 and 3. And then, so we'll pivot, and we'll have to introduce some other ideas to do part 4. But these other ideas sort of end up being fruitful. It turns out sort of the method of part 4, the method you use to see part 4 is also sort of one of the methods you can use to like actually compute rings of integers. And so you introduce sort of, we'll introduce sort of some number attached to a field extension called the discriminant that sort of is related to this proof. Okay, so that's where we're going. Okay, so but let's start with the proof of 1. So just as a warm up, so suppose alpha is in OK. Sorry, so suppose alpha is in K, and I need to show, so there's some, I can multiply it by some rational number and land sort of in OK. So let me write sort of m alpha of x. I'm going to write it the following ways. I'm going to write it, this is going to be x to n plus a n minus 1 over s times x to n minus 1 all the way up to plus a0 over s. Okay, where s, so the AIs are in z, and then I've just sort of chosen some common denominator s for the coefficients. So I've just sort of taking my coefficients, which I know are rational numbers, and I'm taking my coefficients I know are rational numbers, and I'm just choosing a common denominator. And so I can sort of write them like this. And then I'm going to make the substitution y is equal to s times x. So that's the same as saying x is equal to y over s. And I get m alpha of y just by substituting. It's going to be y to the n over s to the n plus a n minus 1 over, well, I'm going to get sort of y to the n minus 1 times s to the n minus 1. I combine that with the s that's already there. I'm going to get s to the n. And then on a n minus 2, I'm going to sort of get s to the n minus 1, and so on, all the way up to a naught over s. Okay, so this is sort of this is not the minimal polynomial of y, because this is just what I got by substituting x is equal to y over s into the minimal polynomial of x. Sorry, this is not the minimal polynomial. Well, let me try again. Sorry, y is supposed to be s times alpha. So okay, let me try this again. Beta is supposed to be s times alpha. That means alpha is equal to beta over s. And then, so the minimal polynomial, sort of, So let me just say it this way. What I was really writing is that beta is a root of m alpha of x over s, so of y over s. Okay. Sorry about that. Yeah, I guess I said this was an easy computation, but it's still a computation, which leaves lots of room to write it down incorrectly. But okay, good. Okay, so this is a polynomial of which beta is root, but then we just sort of multiply it by s to n, and I get sort of m beta of s of y is equal to y to n plus a n minus 1 times s to the n minus 1 times y to the n minus 1 a naught times s to the, sorry, this is supposed to be times s. This is supposed to be a minus 1. Try this again. Multiplying by s to the n, and then here I get s to the n. Okay, but the point is now this is sort of has integer coefficients. So beta is in OK. Okay, so and that's what I had to show for part 1. I just had to show that if I took something in K, if I multiplied it by I could always sort of find some big enough integer, big enough rational number, some rational numbers. So when I multiply by that, I land in OK. So that's an equivalent way of saying this. Okay, so that's the easy part. So let's set up the parts 2 and 3, which is sort of its own interesting thing. And it looks like this locked again. I'm not sure why it's having this problem. Let me try. Okay, if it happens one more time again, I'll try connecting via cable. So I don't normally have this issue. Okay, so right, so we're looking though at parts 2 and 3. So we wanted to show that OK is a subring and that OK is integrally closed. So I haven't defined integrally closed yet, but so I'm going to define these things sort of more generally. Okay, so it's got to do some definitions. That's for many of you will probably be familiar from your algebra classes, but good to recall them. These are some definitions for integral elements. Okay, and by the way, from here on out, rings are always commutative. Unless I say otherwise, rings are always commutative with identity. So just in case your conventions differ from mine. Okay, so good. So suppose R is a subring of S, or I could even just take R to be a ring mapping to S, but let me do it like this. Then we say S in S is integral over R if there is a monic polynomial f of coefficients in R such that f of s is equal to 0. Okay, so that's pretty similar to what I wrote above. When we were working with an extension of Q, so we're looking at sort of things that were sort of integral over Z, I said the minimal polynomial had to have integral coefficients. So when it's not so hard to see that that's actually sort of equivalent to this more general definition in that special case. And that's one of the exercises on the handout this week. Okay, so that's one definition. We say that S is integral over R if every element is integral. We say R is integrally closed in S if sort of the only elements of S integral over R are sort of in R. Okay, and then sort of, well, so that's equivalent to saying the integral closure of R in S is R, where the integral closure of R in S is just everything in S that's integral over R. Okay, so in particular, for R a domain, so if R is an integral domain, we say R is just integrally closed if it is integrally closed in its fraction field. Okay, so maybe some examples. Z is integrally closed. Should be believable from the name at least, and you can check it pretty easily. If if K is a field, then K brackets X is integrally closed. And in fact, any unique factorization domain is integrally closed. And it's essentially the same proof for all of these. And that's also an exercise on your homework this week. Another example, touching back on the introduction of the class. So we look at Z square root of 5. Well, its fraction field is Q square root of 5, but it's not integrally closed. Because, for example, 1 plus square root of 5 over 2 is integral. So this is not in Z square root of 5, but it's a root of x squared minus 2x minus, I'll probably get this wrong, minus 2. So 1 plus square root of 5 times 1 minus square root of 5 is 1 minus 5 minus 4 minus 2. Okay, I think that's, well, close enough. So here the coefficients are in, well, they're in Z. So in particular, Z squared root of 5. Okay, so I mean, this already came up when we were looking at the sort of the ring of integers in Q squared root of 5. We said sort of it wasn't Z squared root of 5, it's sort of Z adjoined 1 plus square root of 5 to 2. Okay, and then sort of this is Y, but and in particular, if you don't add this thing, then what you get is not integrally closed. Okay, another example. If I look at look at the following. So this is, let me look at CXY mod Y squared minus X times, let's say X squared times X minus 1. Okay. So if I look at the element and then sort of its fraction field, so let's write R this, and then looking at its fraction field. And again, this isn't going to be integrally closed. Point is, if I write Z is equal to Y over, if I write Z is equal to Y over X, then so Z, the polynomial Z squared is equal to X minus 1. And so Y squared is equal to X squared times X minus 1. So Y over X is equal to X minus 1. So this satisfies the polynomial. So Z is a root of the polynomial. So this is sort of gets a little confusing because sort of X is sort of used as a variable in the ring, so I shouldn't sort of use it as a polynomial. So my sort of polynomial variable is T here. Okay, but in particular, like this has coefficients. The coefficients are in, well, they're already in sort of C brackets X. Okay, so in particular, sort of they're definitely in R. And in fact, I mean, what's really going on here is if you sort of take the integral closure of sort of this C brackets X inside of the fraction field R, what you get is integral closure, well, either of this thing or of sort of C brackets X is CXZ, where, okay, now and somehow my notation is not great, but I mean, here this is if you treat Z as a variable, and sort of if you, I mean, somehow you can think of it as being a subring of this. Okay, so that's in just a computation you can make by hand again. Okay, I mean, somehow the point is, I mean, these examples are quite close, right? So this is just like frac R is just another way to think about it is it's just I've taken the function field in one variable over the complex numbers and then sort of added a square root of X squared times X minus 1. Well, and then the point, I mean, sort of one way you can sort of understand what's going on in this example as well, of course, that's the same as sort of adding a square root of X minus 1. Okay. Good. So, and there's a geometric, I mean, there's basically a geometric reason for this, and I touched on this a little bit in the introduction. Let me touch on it a little bit again here, and then there's some more about this in the exercises. But the point is, like C of X well, this is contained in C x y mod y squared minus x squared times x minus 1, which is contained in sort of C x z mod z squared minus x minus 1, where here sort of y is sort of identified with x times z. That's sort of how you put this thing in this thing. Okay, and then well, you can, so this is sort of, you can think of these as sort of being all being functions on different things. And so these are sort of polynomial functions on the following spaces. This is sort of this functions on the affine line, like the complex plane. But I'm going to sort of draw it just as a line, so like, because that'll be easier. This is sort of functions on the roots of this polynomial in two-dimensional space. So in that polynomial, it looks, let's see, so it's going to, something like this. And then here, let me make myself some more room. Here, I've got just something like this. Okay, so this is roughly the picture. And then if you sort of think about it, like basically what's happening in this picture is sort of these 2 points are getting glued together. And actually, you can make that completely precise, though we won't. But the main point is this thing that wasn't integrally closed was sort of function. This thing that wasn't integrally closed was naturally functions on a singular curve. I mean, this curve doesn't have a well-defined tangent space at every point, because at this point, like sort of, you sort of want the tangent space to sort of both go in this direction and go in this direction. Whereas sort of the nice thing when you took the integral closure sort of was functions on a smooth curve. So a curve that sort of has a well-defined tangent space at every point. Well, of course, tangent spaces are like something you traditionally make sense of in calculus and sort of analysis, but it turns out you could sort of give a completely algebraic definition of what you mean by a tangent space, and then sort of make this into a precise algebraic statement. And well, there's there's an exercise about this on the worksheet that I have sort of towards the end if people have time to get to it. But even just having this intuition, that sort of this, so this is a good example of like why this is a good definition, like why, like somehow why what you get behaves nicer when you sort of do this, when you define a ring of integers to be sort of this thing that's going to be integrally closed. And it sort of explains why if I sort of disconnect it again. Okay, I'm going to try, sorry, hopefully my future videos will not have as many pauses in them. Let me try plugging in directly to my iPad like this. Let's see if I have better luck with the synchronization. Okay, so what I was saying is, it sort of explains why this is an important part of the theorem, like why being integrally closed is something that's nice that you want to be true. Okay, so heading back down to the bottom. Okay, so those were examples. Want to state, I mean, I want to sort of go back now, sort of prove some things like sort of the integral closures are rings, but let me just state the P lemma, and it's, I mean, it's not even really a lemma, it's just a reinterpretation of the definition of integral. So again, so I have R contained in S, it's an extension of rings, then an element S in S is integral if and only if the subring generated by R and S. So this is again, this means the smallest subring of S that contains both R and this element S. That's one way to think about it. I'll say another way in a second. If only if this subring is finite as an R module. So here, finite as an R module means it's finally generated as an R module, which is very different than being finally generated as sort of an R algebra. So of course, and this is generated by one element S as an R algebra, but it's only finitely generated as an R module if S is integral. So let me prove this. Okay, so let me just remind you another way to think about R of S. So R of S is just the image of the polynomial. So I have take the polynomial ring in one variable over R, and I map it to S by sending sort of, well, it's the identity map on R, and then I just send X to S. To sort of little s. So let me sort of try to make my S bigger. Okay, so I mean, this map exists. This is the universal property of sort of the polynomial algebra. Sort of it's the free R algebra on one element, and sort of what that means is exactly that there's always sort of unique such map. Okay, and well, it's not hard to sort of digest the definitions and see that sort of the smallest subring containing R and S sort of is just the image of this map. Okay, so if S is integral, then there exists sort of an f of x equal a monic polynomial with coefficients in R, such that f of s is equal to 0. But of course, that means f is in the kernel of this map. So then this factors through R brackets x mod f of x, so just modulo ideal generated by f of x to s. Okay, now the point is, this thing is obviously finite as an R module. This is finite as an R module. Okay, so that's one direction. So that says if S is integral, then write like this. This is finite as an R module. So if S is integral, then R brackets S is finally generated because you take just sort of generators over here and they give you generators over here. And of course, the generators over here are sort of x to n minus 1, x to n minus 2, all the way through 1. So that maps to sort of s to n minus 1, s to n minus 2, so on, down to 1. Okay, so that's sort of one direction. Good, so then in the other direction, oops, sorry, can you get, okay, good, that's still seeing. One. Okay, so in the other direction, so if Rs is finite, then, well, there are generators, let's call them B1 through Bm, then sort of each of these sort of is an R linear combination of sort of the S to the I of powers of S. And since there are only finitely many of them, well, there's sort of some highest power of S appearing in those combinations, only finitely many. So this implies that sort of S to 1S S squared, S cubed, so all the way up to S to sort of some big power N is also a generating set. So just as an R module. Again, I'm not saying anything about it being free or anything. I'm just saying that it's generated by these elements as an R module. So sort of anything is sort of an R linear combination. And again, the argument is just sort of if it's a finite R module, then sort of has some finite set of generators, but each of those sort of, for example, by this description up here, can be expressed as sort of just a finite polynomial in the S's in S, and then sort of there's only finite many powers appearing. So in fact, sort of these things form a generating set. Okay, but then that means since S to the N plus 1 is in here, this is going to be equal to sort of AN times S to the N plus AN times A N minus 1 times S to N minus 1, and so on, all the way up to plus A0 times 1 for AI in R. Okay, and so that implies everywhere these are little s's. So that is a polynomial that is that is a monic in polynomial with integral with coefficients in R satisfied by S. S, the polynomial is subtract. Okay, so S is integral. Okay, good. So that's that finishes the proof of the lemma. Let me just recall sort of what that lemma said. So that lemma sort of took this statement about sort of there existing some polynomial, and it turned it into sort of a more, somehow it turned it into a sort of more module theoretic statement. And the reason that's going to be useful is because we have sort of some tools for understanding sort of when we have some tools for understanding sort of finite R modules. So in particular, everything we'll do next will sort of basically use that finite R modules are sort of closed undertaking submodules when you work over a Noetherian ring. So that's sort of how we're going to get some mileage out of this characterization. Okay, so and let me state sort of the proposition that generalizes sort of parts 2 and 3 of that theorem we started with. So here, part 1, say if R and S, then the integral closure of R in S is a subring of S. Let me just sort of point out if I take R to be equal to Z and S to be equal to K, a finite extension over Q. So K is a field, finite over Q. then sort of the integral closure is what I defined to be okay. And so this gives part 2 of the main theorem. So part 2 of the main theorem was what said that okay was that said that so this ring of integers okay really was a ring. And then the second statement is that if I have a chain of extensions, so R is a ring that's contained in a different ring S, which is contained in a different ring T, and then if S is integral over R, that means just every element of this ring S is integral over R. And T and T is integral over S. Then T is also integral over R. Okay, so this is going to give part 3 of the theorem, which said that OK was integrally closed. Let me do that. So if R is equal to Z, S is equal to OK, and then T is equal to K. So again, we have K, Q, my extension. Then this gives part 3 of the main theorem. So that part 3 said that OK was integrally closed. Sorry, so let me just point out, so the K is equal to fraction of OK. So we already know, once we know part 1, we know OK is the subring of K, and sort of combined with, sorry, once we know part 2, yeah. So once we know this statement, this is part 2 of the main theorem, that OK is a subring, then sort of part 1 of the main theorem told us that sort of OK times Q was equal to K. So we know that sort of K is the fraction field of OK. But then this theorem will now tell us that OK is integrally closed. And because if you sort of, and this theorem says if you have something that's integral over OK, then it's in fact integral over Z, but then it was already sort of in OK. Okay, so that's this general statement. So let's talk about the proof. Yeah, and by the way, I should say there are different ways of proving this statement, and there are different ways of, and there are also sort of different ways, like sort of go through this to varying degrees to prove the original sort of the main theorems about rings of integers and finite extensions of Q. And so some of those are discussed in the exercise and in Milne's notes, for example. But I like the one I'm about to give because it's sort of, it's a good example of how to use commutative algebra effectively, and like the kind of techniques that are sort of useful later too. So I'm only going to prove one. So I'm only going to prove that the integral closure of R in S is a subring of S. But the proof of 2 is very similar. So if you understand the idea that's going into the proof of 1, then you can sort of, you'll be able to carry out the proof of 2 on your own. Okay, and so here, in proving this theorem, the main idea is to sort of prove it for a Noetherian ring first, and then sort of realize that you only needed to prove it for a Noetherian ring. So let me sort of prove it for a Noetherian ring. I suppose R is Noetherian. Okay, and let me take me write sort of R tilde for the integral closure of R and S. And I want to show that it's a subring. So right now I just know it's a subset. I want to show it's a subring. Well, let me take sort of A, B in R tilde. And well, let me just look at R adjoin, so the smallest subring of S that contains both A and B. So this contains in it small subring that contains A plus B, as well as a small subring that contains A times B. And of course, what do I need to do to show this is a subring? I just need to show that R tilde contains A plus B and A times B. So I need to show both of these are integral. I need to show A plus B and A times B are integral, but that's the same as showing, by the lemma, that's the same as showing these modules are finite over R. Okay, the point is though, this R adjoint AB, this in either sort of from the lemma or just in looking directly at how we prove the lemma, you can see this is finite, a finite R module. Generated by sort of A to the K times B to the L, where sort of K and L are both less than equal to some sufficiently large number N. That sort of, you can take this N to be the degree of the polynomial, like the bigger of the degree of sort of some integral polynomial satisfied by either of these. Okay, so that's easy to see. Okay, but this is a finite R module, and then R is a Noetherian ring, so any submodule is also finite. So R is Noetherian. So it implies submodules are also finite. So the lemma gives that that A plus B and A times B are integral. Okay, so that's the proof when R is Noetherian. And of course, the statement isn't true for a non-Noetherian ring, right? I mean, for a non-Noetherian ring, you can have a finitely generated module. You can have a finite R module and then a submodule inside of it that's not finite. So this really used, so as I said, this really used the fact that R was Noetherian to deduce this. Okay, and there are sort of other ways you could do, maybe with some minor assumptions, you can actually sort of directly produce a polynomial, the A plus B, or sort of A times B. Well, okay, let me, and this is in the exercises, let me not say some more about that. Instead, let me just sort of talk about how you reduce to the Noetherian case. So are not necessarily Noetherian. Well, let me sort of still take A, B inside of R tilde. And okay, and so then let me take sort of F, G in Rx monic, such that F of A is equal to 0 and G of B is equal to 0. Okay, and then let me sort of, so F is equal to x to the n plus a n minus 1, x to the n minus 1, so on, so a0, and then G is going to be x to the m plus a, let's say b m minus 1, x to the m minus 1, and so on all the way up to b0. Okay, and the point is now inside of R, so inside of R, I have the subring generated by these coefficients. So I can look at just Z. So the subrings are over Z generated by A0, A1 to AM minus 1, and B0, or sorry, AN minus 1, B0, B1 to BM minus 1. So let me call this, call it capital A. So capital A lives inside of R, it lives inside of S. And because I sort of stuck all these coefficients in here, I mean, it's still true that A and B are monic. A and B are integral over A, over this capital A. These two elements that I started with integral over R, they're also integral over the subrings, because I stuck in all the coefficients that I needed to make them integral. But A is Noetherian. So A plus B and AB are integral over A by the previous argument. Which implies they're integral over R, because A is just a subring of R. Yes, and so this ring is Noetherian because it's finally generated over Z. This is a standard result about Noetherian rings. So we can take a finally generated ring over any Noetherian ring, and it's still Noetherian. Okay, and so somehow, yeah, and the point in this step 2 is just to observe that, like, when you're checking sort of that this integral closure is a subring, I mean, checking that only ever involves finitely many elements at the same time. And so sort of this is like an important, very useful concept, like in ring theory, number theory, algebraic geometry, and in general, it's just, I mean, oftentimes, even if you find yourself working with very big infinite things, like if your computation only involves finitely many of those things, like you can probably sort of assume you're actually in a Noetherian setting. That's a very, very powerful technique from time to time. For example, here. And this is relatively painful. And the other proofs aren't complicated, but this proof is sort of particularly painless. I think so. I sort of dodged doing any actual computations. Okay, good. So that's right. So that's just where are we at? So that proved this part 1 of the proposition. I already said sort of part 2 of the proposition sort of is along the same lines. And again, the point is part 2 again will be sort of simple in the Noetherian setting, and then it's a statement that only ever involves finitely many things at once. So you can sort of reduce to the Noetherian setting. It's not going to be a proposition that covers sort of parts 2 and 3 of the main theorem. So let me sort of scroll back up to the main theorem so we can see where we're at. Okay, so we did part 1, that was the easy thing. We did part 2 and part 3 now. So we saw OK is a subring of K and that it's integrally closed. Sort of followed from that sort of much more general statement about integral closures and rings. And so this is sort of just a very general commutative algebra statement. But now we need to see this last part. We need to see that OK is a free Z module of rank K over Q. Okay. So, and by the way, if you're trying to break this up into two, like watching in 2 different points, and you sort of are still with me, then this is probably a good point to like sort of stop, and then you could come back for this part later. So, so how to see that sort of we're in this setting where we have, and I better write down the setting again just because we're sort of mired in generalities for a minute. So I'm back in just a finite extension of Q. Now I see that OK is, and really I just want to see that OK is finally generated. It's a finite Z module. Again, not finally generated as a ring, but as a Z module. Okay, so so when I say finite Z module, that means sort of finitely generated as a Z module. Somehow, usually we just write finite because you want to sort of avoid sort of confusing it with finally generated in algebra. Of course, here you could confuse it with just being like finite as a set, but that's not what this means. This means finite, finitely generated as a Z module. Okay, and so and just again, I said this at the start, but let me sort of remark, like this is enough for part 4. So we know it's torsion free. So it's torsion free, and so then it's finally generated. And so by the structure theorem for modules over a PID, this is just, Z modules are just abelian groups. So even just for abelian groups. So that will say it's free. So I said structure theorem for modules over PID, but of course, there's a structure theorem for finally generated modules. So that says it's free, and then sort of if you combine that with part 1, it's not too hard to see that sort of its rank has to be the same as the degree of K over Q. So that's all we have to see. We have to see OK is finally generated. And again, sort of as I sort of said at the start, and this is sort of surprisingly subtle. Okay, and so, and the idea, and again, one of the reasons I wanted to use sort of a Noetherian ring argument for this previous thing, even though there's sort of options that sort of don't make a Noetherian argument for sort of proving that OK is a subring, is because we're about to use sort of a Noetherian argument again. So it suffices. So and a key idea is sort of it just suffices to put OK inside some finitely generated, some finite Z module. Sort of inside of K. So again, this is because Z is Noetherian. So if you have a submodule of finitely generated module over a Noetherian ring, then it too is finitely generated. Okay, so that's how we're going to do it. But we're going to need some extra structure that we haven't talked about so far. So let me just sort of say, like in your algebra class, so here's some philosophy. So in your graduate algebra class or undergraduate algebra, any algebra class, hopefully. So you saw the power of thinking of sort of a field extension. You have some field extension K over Q just as a vector space. Or let me say it this way. Just L over K as a vector space. And that's like, this is how you define degree. So like if L over K is a field extension, in particular, L is a K vector space. And if and so you can just take the degree to be the dimension of that K vector space. And degree sort of encoded all sorts of useful properties. It's very rigid. It sort of multiplies in towers. And this ends up being sort of a key tool to how we investigated fields in an algebra class. But it turns out there's sort of something else intermediary between a field and a vector space. So you can sort of forget some structure while still sort of remembering some other piece that lives in the world of linear algebra. So here in sort of graduate number theory, we'll use that this is only going to work for separable field extension over K is naturally equipped with a non-degenerate bilinear form. So, I mean, like a bilinear form, like in the sense like that you saw in your linear algebra classes, like an inner product on a real vector space. I mean, this won't be an inner product because it won't sort of satisfy that positivity, but a non-degenerate is sort of good enough for most things. So I'll say more about what that means in a second. But this is going to be a very powerful idea. So somehow, instead of going all the way to just thinking of it as only a vector space, we're going to think of it as a vector space equipped with a bilinear form. And like that still lives in the world of linear algebra, but that's going to give us some extra mileage. And that extra mileage will let us sort of prove, let's prove that OK is fine as a Z module sort of when K, sort of when we're base field is Q and sort of we're looking at some finite extension. Okay, so how do we do that? Well, let me first describe what this non-degenerate bilinear form is. And I'm just, so on the homework, or also on the exercises, we'll go into this sort of for an arbitrary extension L over K. So I'm just going to do it sort of in the setting we're most interested in right now, which is just an extension of Q. And somehow there are lots of subtleties that you can sort of ignore over Q. Then this sort of already covers sort of a lot of what's of interest to us. So it'll be easier to start that way. So, okay, so we have K over Q, a finite extension. Okay, and then if I have some element alpha contained in K, well, I can think about just multiplying by alpha. So I can think about just multiplying by alpha, and this is a linear transformation of Q vector space. So let me say this is a Q linear transformation. Just because multiplication is sort of commutative in K. So this is a Q linear transformation. So if I think of K as a Q vector space, then multiplication by some element field is a linear transformation. Well, and I can take the trace of that linear transformation. So I can take, and the notation is trace K over Q of alpha is just the trace of this linear transformation. So, and one way to think about it, this well, that's the sum of the eigenvalues, the sum of all the eigenvalues in an algebraic closure. That's sort of too fancy a way to think about it. This is just the, like if you write down a basis for K as a Q vector space and then write down the matrix of alpha, then you're just adding up the entries on the diagonal. Okay, so good. So, and this is sort of satisfies lots of nice properties. I mean, it's sort of additive. Like a trace of alpha plus beta is trace of alpha plus trace of beta, and so on. So we'll see some other things, but well, let me write that down. And then sort of also multiplies. So trace of K over Q of C times alpha equal to C times trace K over Q alpha if C is in Q. So if C is in the base field, and this isn't true, I mean, sort of this wouldn't make sense because this traceless linear formation. So this is a map. So I should say, and trace K over Q. This goes from K So I'm taking the trace of a linear transformation sort of on a Q vector space. That's a rational number. So of course, it wouldn't make sense to ask that it be multiplicative for an arbitrary element of K, but it is true multiplicative sort of for scalars. And for both of these, you can just sort of write down a basis. And you can see this. Okay, yeah, let me not get into that. Let me say, in particular, trace K over Q of 1. Well, that's just multiplication by 1 is just the identity matrix, and it's the identity transformation. So that's a trace of the identity transformation from K to K. And the trace of the identity transformation, well, in any basis, that's just going to be the identity matrix. So that's just the dimension of the vector space, which is K, which is a degree. Okay. So in particular, yeah, that's fine, actually. Let's just say it like that. Okay. So then using this, I get a bilinear form on K called the trace pairing, which is defined by so the pairing of alpha and beta is the trace of alpha times beta. Okay, and so if you look at these identities in the example and then sort of just the rules for multiplication of the field, you can easily check this sort of is a bilinear form. So this is a Q bilinear form. So there's a bilinear form on this Q vector space with values in Q. Okay, so how does this help us? And we wanted to show that the ring of integers OK is finally generated. So we want to show it's a finite Z module. And so, okay, so how are we going to do this? We're going to do the following. Oh, yes, right, I guess I should say non-degenerate. And it's even symmetric because trace of alpha beta is always trace of beta alpha. And then it doesn't really matter it's symmetric, but it is. So it's non-degenerate. This is sort of the key part because I take alpha times alpha inverse over the degree of extension. This is just trace of 1 over the degree of extension. Which is 1 over the degree of extension. Times, there's not really any reason I had to do. I guess there wasn't really any reason I had to normalize like this, but that's fine. But this is K over the degree over the degree, which is equal to 1. So being non-degenerate, that just means sort of any element, for any element, there's sort of some other element that it pairs with that's non-zero. Okay, so and what does this mean? This means the map from K to its dual vector space, which is Q linear homomorphisms from K to Q. So it's dual vector space that just sends sort of alpha to the linear map that's pairing with alpha. So this sends beta to inner product of alpha and beta. Again, here, like this part, all this part has nothing to do with sort of the specific bilinear form I have. This part's completely general. This is an isomorphism. Well, it's injective, thus an isomorphism. Because they have the same dimension. So this map is injective because sort of saying this injective says sort of anything over here should go to sort of some non-zero functional in K. But I know that sort of pairing with alpha is non-zero because I can find something that it pairs with to give 1. So that map isn't 0. So that means this is injective. And then but it's an injective linear transformation from K to K dual. Just as, again, if these are vector spaces, and those have the same dimension, so it's an isomorphism of vector spaces. Okay, so this is sort of how this non-degeneracy will get used in a moment. Okay, so that's where we're at. We've seen that sort of we don't just equip a finite extension of Q with like it's not just sort of a vector space, it's a vector space with this natural non-degenerate bilinear pairing. Okay, so let's use that. So we have let's take a basis let's say E1 En for K as a Q vector space. Okay, and then sort of by part 1 of the main theorem, so if I multiply them by some large enough integer, I can assume they're all in OK. So I can assume that EI is contained in OK. Okay, so then good. Okay, so now I'm going to look at sort of the subring. Oops. I don't know what just happened there. Okay, so that's back. So I'm going to look at the subring. Or sorry, the subring, just the submodule. So let me call it just M. I actually, a little premature, sorry. So these EI are contained in OK. I'm going to look at a submodule in a second, but I forgot to introduce what I actually need to span that submodule. And so I'm going to let Fi be the dual basis. So, and what does that mean? And so the dual basis is the basis for sort of the dual space, so the dual vector space. And then Fi is just sort of thing that just sends EI to 1 and sort of EJ for I not equal to J to 0. But the point is, because we have this fixed bilinear pairing, this non-degenerate bilinear pairing, we have an identification of the dual space sort of with K itself. So we have this identification, the dual space with K. So that means I can think of the dual basis as being elements of K. So what this means is sort of Fi are in K such that if I pair Fi with EI, sorry, Fi with EJ, this is equal to 1 if I equals 0, sorry, if I equals J, and 0 otherwise. 0 if I is not equal to J. Okay. Okay, good. So the point is now I claim that OK is inside the finally generated submodule, so the submodule generated by these. Okay, I mean, well, and how do I do that? And I just have to express an element of OK. And I just have to sort of see how to express an element of OK in terms of this basis. So, but for any alpha in K, and this is just the basis, and so using this, and by definition, alpha is going to be equal to the sum of sort of the inner product of EI with alpha times FI. I mean, somehow this is just a reinterpretation of what it means for this to be the dual basis under this pairing. Okay, so I'll leave that as something to be worked out on your own. But now, sort of, this is just the sum of the trace of EI times alpha times FI. Okay, and so if alpha is an OK, then EI times alpha is also an OK, because sort of by definition, and by choice, EI was an OK. The space to start with was an OK, and OK is a ring. But in fact, sort of what we can check is that sort of the trace of sort of anything in OK is actually in Z. So this implies trace of EI times alpha is train Z, which is what we needed. Okay, so yeah, and this comes from the relation between sort of trace and sort of characteristic polynomial. And somehow, not surprising, there's a close relation between the trace and the minimal polynomial. And in particular, since we know the minimal polynomial of any integer is has coefficients in Z, we'll find that sort of the trace is also in Z. So the specifics of that computation are again on the exercises. So the relation between the minimal polynomial and this trace. Good. So that will conclude the proof of finiteness, because sort of we put OK inside this finally generated Z module. And again, Z is Noetherian, so that means OK is finally generated. So this sort of finishes part 4 of the theorem. Okay, so there's just a little bit more I want to say, sort of building on this part, sort of building on this computation. When we actually get a pretty useful numerical invariant. So let me just set up final definition. We'll use a fun color for the last 10 minutes. So maybe orange is a fun color. So say V is a Q vector space. So a finite dimensional Q vector space. And then with a non-degenerate bilinear pairing. And then we have sort of M inside of V is a lattice, so a Z lattice. This is free Z module. Sort of finite rank that generates V as a vector space. So, and this is again an exercise, and what's easy to see that in this past that we have rank equal to the dimension of V. Okay, then we sort of define M dual to just be, and it's maybe not the best notation, but this is just sort of all M contained in V such that so let me say all sort of F contained in V such that F M is contained in Z for all M. So Fm is contained in Z for all M and M. Okay, and so this is again going to be a free Z module. Okay, and so it turns out to be interesting to look at sort of M. Yeah, let me say. So sort of interesting to think about M that are contained in their dual and look at the sort of the size of the quotient. So this is going to be sort of some positive integer. So in particular, I'm going to apply this to sort of OK, so living inside of K. So this is a lattice in K. You want to look at the dual. So sort of everything who's sort of trace pairing with OK gives you an integer. And you're sort of looking at the difference between OK and OK dual. So, and sort of same argument we saw just above, sort of will show that OK is contained in sort of OK dual. So we want to look at that, and so this absolute value. So let me sorry, I wrote this quotient in the wrong way. So M dual mod M. So OK dual mod OK. So the size of this quotient group, we're going to call the absolute value of the discriminant of OK. So discriminant of OK over Z, or sometimes we'll write discriminant of K over Q. So, and what this discriminant actually is going to be and what this discriminant is going to be is just a way of computing this. So then it turns out sort of we can refine this a little bit and actually get a genuine integer with an interesting sign whose absolute value sort of gives this number. Okay, and I think so. There's a standard way to do this. Let me just say. Yeah. And somehow we want to sort of compute the index of M dual and M. So in M, let me say it this way. So OK here is a free Z module. Yeah, here I could use sort of any M, but let me do it with OK. Free Z module. So let me sort of choose a basis. So E1 through En. Okay, so I'm using that I now know OK is a free Z module of sort of rank equal to K on Q. So N is equal to degree of K over Q. So I have this free Z module, I have this basis, and then I sort of take the dual basis. Well, and then sort of just in terms of vector space, like the dual basis, in the sense I sort of wrote above, but then sort of OK dual is just going to be sort of this lattice I looked at before, Z F1, and yeah, just the last span by these guys. Okay, and so then the quotient OK dual mod OK, just by like completely standard facts about Z modules, I guess, about abelian groups, or just really about linear algebra. The size of this quotient, you can compute it as sort of the determinant of that's the value of the determinant of the change of basis matrix from sort of F1, some FIs to EIs. I mean, so the point is, this determinant, like if you were to sort of change your basis for OK or your change basis for OK dual, you're no longer required to be like the dual base of each other. You're going to be changing by an element matrix in GL2Z, and so your determinant's going to be plus or minus 1, so it's not going to change the absolute value. So sort of instead of taking like this basis and the dual basis, you could sort of just take and then like sort of the adapted basis you get from the fundamental theorem of modules for PID, and then this is like, and then this is a completely elementary computation. But then we're just going to use sort of this and this thing and its dual basis. And the point is sort of the number you get. So this thing inside of here is called the discriminant. And this discriminant is, well, we know it's absolute value, but in fact, its sign also doesn't change. Like if I change a basis, if I choose my basis E1 through En, and then sort of take the dual basis, so if I change this basis, then that also changes the dual basis. And so those two changes will cancel out sort of the sign change that you would have. So again, this is going to be in an exercise. But this is the discriminant, and but we can write down this matrix. So this is just the determinant of the matrix of trace EI, EJ, sort of for any basis. Okay, and so in the exercises, we'll develop a lot more about this, but this sort of ends up being a pretty important number. So it's a good exercise to sort of see why this is the change to the basis matrix. But it's very similar to the computation we just did above. But yeah, and so this ends up being a super important number. Sort of tells you a lot about sort of the geometry and the arithmetic of this of this field extension, sort of how that reflects in the rings of integers. So we'll do a lot with this. Okay, but I'm going to stop there. Sorry for the technical difficulties at the start, and I'll see everybody in class on Tuesday and Thursday.